Yes, sir. Will do, sir.
So we'll have a small recap on what we have seen in the last class. We have seen this Bayesian classifier. What actually the thing over here is, we'll be given data is similar to what the things we'll be doing with decision tree classifier. It is also possible using Bayesian classifier. We just say only one thing. Decision tree classifier is derivated from the Bayesian classifier to perform something more. Right? When you do something with decision tree classifier, it will perform better. But the root of the decision tree actually came from something called as the conditional probability theorem or the Bayes theorem. From Bayes theorem only it is actually evolved. So what you say is actually take some data set, you give some probability to each of the items. For example, if I have some data to be classified, I want this to be in discrete. Yes, it is discrete. Yes and no. You take the total probability of those positive and negative data items, and you take the conditional probability. That is, conditional probability says that what is the probability of the total positive outcome given any particular future outcome to get exist. For example, I will say what is the probability of yes given one of my futures say outlook is going to be sunny or it is going to be overcast or rain. So I'll be giving some probability with respect to a condition. If that condition exists, what will be the probability for my positive outcome? If this condition exists, what will be the probability for my negative outcome? So that is what I need to calculate. So this I will represent as the degree one conditional probability. The degree one says that I'm going to take consider only one condition. But in Bayesian theorem, it is not about the constraint for degree. If you increase the amount of degree, the amount of degree says that if you make more conditions here I have outlook equal to sunny, temperature equal cool, humidity equal high, wind is equal to strong. I have a 4-degree feature. So if this the degree increases, then the complexity of the model increases. It doesn't mean that you do not include many features into the set. It is that you have a limited amount of features that essentially will classify the particular output. Right? That is the thing over here. So this should not be as low as possible also, and it should not be as high also. So you should have a medium rate for this degree. And the formula for Bayes is going to be V and B is equal to R max of V belong to S or no. I'm having two output labels, one is yes and other is no. I'm having the total probability, that is P of V tends to S or V tends to no, whatever this that is going to be over here, into product of all individual conditional probabilities. So all the degree one probabilities I'm going to take and then I multiply them all together. So this is actually the probability of S. Similarly, I'll take the probability of no for each of the individual probability multiplications into the negative probability. Then what I'll do, I'll take the argument max, which I have two arguments. One is S argument, and I'll take that as the record. So I say 0.2057 is highest compared to 0.0052. 0.2057 corresponds to a no item. So I say rate n is will be equal to no if this condition is actually exists. So this is the prediction that is obtained when I have this particular conditional state. This is the Bayesian theory. Now, what is the plan for today is we'll be taking the same data set. Let us go for one more condition and using that particular condition I'll be taking it and I'll be solving the same. Yes. So I'm making it clear the Bayesian probability theorem. If I give anything like this to you, will you be able to do it on the conditional probability? I'll be giving is I'll be giving a data set like this, and I'll be asking you either to find if it is a very quick answer to the question. I'll be asking you this degree one probabilities. Else, if it is a more than two, then I'll be asking these kind of questions. In somewhat bigger quizzes, I may ask this particular kind. I will extend the degree, and then I'll be asking these things, right? Whether this will be easy or it will be tough, or you able to solve in 2 minutes like that. Want to ask two times, huh?
We can solve it, sir, by using Bayes theorem.
Yes. So if I give any questions like this, you'll be able to solve, right? That is the thing. This is with respect to quizzes, I'm saying. Now, the same thing what I'm going to ask you is, I'll be giving a data set like this. I have that also ready. Yesterday we actually solved this decision trees, and many people, I hope Yugandhar, Akshit, and Akshot, Pavani, anybody actually solved the Pujita also, or solved it with the accuracy level. And I think Pujita got 80 percentage. I hope some. She actually, right? Pujita, you are only right. You messaged me. Yeah?
60%, sir.
60%.
60.
Yes, 60%. Yes, so you messaged me. So based on that, I also have that. So what is the extension over here is for the same data set, for the same feature, for the same output variable classification, how Bayesian is going to react, right? So that is the thing we are going to see. Before that, let us solve one more example on this with some other condition, and we'll be going into that particular problem, right? Now just write the degree. You just say me what will be the classification. Okay. So let me write the degree conditions. Let me say outlook is equal to rain. Let me see what are the things available. Temperature, comma. Temperature is equal to mild, comma. Humidity equal normal, comma. Wind equal strong. Right. So this is the data I gave you. Now we have to identify what will be the Bayesian classification for this thing. Right. So I ask you classify whether date n is either yes or no. Right. You have to classify this answer. Right. Now shall you say what will be the procedure? We want to classify this the formula.
First, we will see what is the given value, sir, for yes.
Given values in the sense
We need to find P of A, right? P
yes
of
degree one probability. Right.
degree 1 probability, we need to find P of
Yes.
B is already given probability.
Yes. So degree
Given
one
probability
probability
we
I
need
have
to
this.
if the rainy means 3 by 9 in yes case, if we are doing in no case means we are taking the raining probability as 2 by 5. First of all, we will do S case S probability, right? So we are taking 3 by 9 as our P of B.
Okay, great. Exact answers. So I have the degree one probability already computed for the same data set, and I have the total probability also. As you can rightly said, first I need to take for S, and then I can compute fully for S. Then I go for no. Then I take the argument max and say for which it is having the highest probability. I'll rate that yes or no. Right. So let I take S first. So P underscore S. P of S is equal to, so I take the probability of S, I have this probability into probability of outlook is equal to, what is outlook? Rain. Outlook is equal to rain. So I go and see, first let us write the thing. Outlook is equal to rain given as, next what is the next thing what we are given? Probability of
Temp- Temperate,
temperature. Yes, temperature is equal to
mild, mild,
mild given as next probability of uh, humidity. Humidity equal normal given as into probability of wind equal strong given as. So we have the individual probabilities already ready. So I take the individual probability items. So what is P of S? I go above. P of S is 9 by 14, and probability of rain given S is 3 by 9, and probability of uh, temperature equal to mild given as 4 by 9. Sorry, I'll remember these two. 9 by 14, 3 by 9, 4 by 9. 9 by 14, 3 by 9, and 4
4
by
by
9. And humidity equals normal.
6 by 9, I think.
Is correct. 6 by 9. And wind is equal to strong is again 3 by 9 into 6 by 9 into 3 by 9. So let me take the calculator. Okay. 9 by 14 into 3 by 9 into 4 by 9 into 6 by 9 into 3 by 9 is 1 point. No, how 1 point will go? Made some mistake. 9 by 14 into 3 by 9 into 4 by 9 into 6 by 9 into 3 by 9. 0.0211. Is it right? Is it right?
Yes, sir. Right, sir.
Now we have the same thing. I will be doing for v underscore vs also. So we know also. So we know will be probability of no into probability of outlook.
Oh,
Same conditions I write. Probability of outlook is
rain,
equal to
comma, no. Rain
wait,
given, no.
wait, rain given no
No.
into
Temperature. Probability
probability
of
of temperature
mild given, no.
equal to mild given no
Into
into
probability of humidity. Humidity.
into probability of
Wind.
wind equals strong given no. So let me go up and sign the degree 1 probabilities.
P of
This is
no.
5 by 14 and the rain no will be 2 by 5. Mild no will be again 2 by 5. Humidity normal 1 by 5. So 2 by 5, 2 by 5, 1 by 5
Zero.
equals 5 by 14 into 2 by 5,
2 by 5 into 2 by 5.
2 by 5
1 by 4.
into 1 by
4.
1/5, sir.
again also 1 by 5. Strong is 3 by 5.
3 by 5.
Yes, yes. So now I'll take the calculator again. 5 by 14, 5 by 14 into 2 by 5 into 2 by 5 into 1 by 5 into 3 by 5. 0.0068. Alright. Yes, now I take the argmax. So what will be my V under V NB now? V naive Bayes classifier will be equal to argmax of V of S, comma V of no.
No.
So I'll be taking argmax of 0.0211, comma 0.0068. So compared to 0.02 and 0.00, so 0.02 is highest. So what I can say,
Yes.
for the given
I will
condition,
play tennis.
Yes, correct. Outlook is equal to rain. Uh, Temperature is equal to mild. Humidity equals normal. And wind equals strong. The classifiers, Bayesian classifier is Clayton is equals yes. Thing. How much time will happen? Whether if I ask this for some 2 marks, then quizzes, it will be easier, or it will take more than 2 minutes. Okay, I'm asking you. So afterwards, you should not say the time is not there when we go on the right. Anyway,
3 minutes.
Anyway, options will be there.
3 minutes.
12 minutes we should not give na after all.
3.5.
Right?
No. 3.5 na we should not give this one within 2 minutes only solved. Now we can give it for this.
Quiz
Let
is
me see.
over, na, sir.
Huh?
Easy thing, sir, but time taking, sir. Calculation, and we need to see that.
Quiz is
It's
already
conduct.
finished, na, sir.
Yes, our quiz is finished. Yes.
Sir, who
So,
is that boy, sir? In rain also he will go to play.
in train, wind actually rain is there. Temperature is mild only na. Temperature is not cool na, and humidity is also normal. These two
Strong
are
wind,
positive.
sir. Sir, if tennis while playing tennis, wind is strong means the ball will go off, right? How can he play tennis, sir?
He is very. He's having a very huge arms, so he can actually beat that. Okay. So now the Bayesian classifier is fine. Now what I'll do is I'll go to the decision trees example. So I have my ODI data over here, right? So this ODI data, what it does, we actually took this in the yesterday's laboratory session. We have the match results for different ODI matches, and with these ODI matches, what we have actually done, we have taken who is the winner, and we converted the match result value as if a host is winning the match, then result is 1. If the host is losing the match, then the result is 0. How to find host in the match? If I have Australia versus England, then Australia is the host, because always host name will be given first. Here New Zealand versus Pakistan means that New Zealand is going to be the host. So likewise I'll be doing. If New Zealand is a host and New Zealand wins a match, then I put result as 1. If India is the host and West Indies wins, what I'll put here?
0.
0. So in this way, I have actually done the data, and finally with what Shirdi said, we also took the opponent also. So this opponent data also we took. We converted everything into discrete numerical values, and we experimented the same. So with this, we actually done the thing. We done it, and I asked you to do the training and testing also for this to predict the accuracy. So what I did, I also experimented the training and testing. What I did is very simple. Just from sklearn dot model selection import train test split, then from sklearn import metrics. These two things I took. From this I actually used this particular statement, that is x train comma x test comma y train comma y test, which will be equal to train underscore test underscore split of the input x, output y, test size as 30% and random state as some numerical number. Now I give here addition tree dot fit. Then this is the extra here, instead of giving capital X comma Y, I gave X train comma Y train. Then what I say, with this particular model D tree, predict the X test, or predict the Y test from the X test. I don't give the Y test to my model. Instead of giving Y test directly, I gave the X test alone and ask it to predict the Y test. So that is called as Y predict. Then I take the accuracy, that is matrix dot accuracy underscore score. I compare the what is the original y test value and what is the predicted y value I take. I compare both and give the accuracy of the model. And as Pujita says, it is around 0.649, around 0.65, 65%. This is same, right, Pujita?
Yes, sir. 60% I got, sir.
Yes. So this is the thing, right? Now we got this. Now we can use this Bayesian classifier what we used for RRR over here also, right? So I take the Bayesian classifier. I got a new cell. So for the same data set, I have the X train ready, I have the Y train ready, and for this X stage, I need to predict the result, right? So just for our understanding, let us print and see the X train alone, so that whether it is running RRR or whether it runs cricket, we will understand. Yes, it is running cricket only. Accuracy is C 0.516. 0.516. The accuracy over the decision trees is around 0.649. So this is the difference you are actually recurring, right? When I use Gaussian Naive-Bayes algorithm, I am getting an accuracy level for classification of match outcome. I am getting here 0.516. So this is actually what I am willing to compare is three things to consider here. One is decision trees is actually an evolutionary algorithm. Decision actually is an evolution of Bayesian conditional probability theorem only. But since decision trees make use of those entropy, information gain, and Gini, those kind of metrics, it is actually improved. It is an improved version of Bayes. But over here in Bayes, it also has some advantages for particular kind of data set which is not sparsely located. So we say some data set as sparse data set, some data set as dense data set. So what is a sparse data set in the sense? For a particular outcome alone, there will be more number of input supporting, and for the other outcome, there may not be more input support. A dense data set in the sense for all the outputs, I'll be having more support for both input and output. So we say more more clarity. Say for example, for the match outcome being yes, or a match result being 1, many inputs are there to say that it is always 1, and only some input will be there to say it is 0. Then I say that the data set is actually biased over positive and negative value. It is biased for positive, means that it is fully having many input records supporting the one value. And if it is sparse, and it is sparse for 0 values, right? So what we can actually do is, if the data set is more sparse, at that kind of time we can use decision trees. If the data set is more dense, then we can use Bayesian. Why we should not use sparse data set for Bayesian is, Bayesian is purely related on conditional probability. If I take the data set as sparse, for example, if more number of data set is going to support 1 and only very few inputs are going to support no, and if I take the conditional probability, all the time the answer will be yes only. There will not be any answer supporting for no. Every time I run it again and again, I'll get S only, because it is highly biased. The data set is highly biased. This problem will not occur in k nearest neighbors. Why? Because in k nearest neighbors, if I increase the k value, that problem may be solved. But in decision trees and in decision trees also, I may consider those as some impurities or some biased data, and then I can neglect. So those things are actually available. So that is actually the difference, right? You keep this in mind, right? Now I want you guys to include this particular cell data also to your decision tree collab exercise. And if suppose, and this is actually our next exercise also, I hope I'll open our lab manual. So I think this is our first next exercise also, I hope. This is the decision tree exercises over here. That is, you can take something like who is host, task, even rank of the player ratings, among others. These are key factors. And I need to find the decision trees and describe the route. So we have the decision tree ready, and we can describe the route. We have done that. Next is over here. In many ways also, the same problem statement is given for the same house task ratings. Model the prediction using Bayes algorithm. We have this, and there is some conditions also given. You take the matches between 2018 to 2020. So those kind of conditions are given. You can put that condition while querying the ESPN frequency. So that is actually the prediction. So what you can actually do is, in next exercise, if you see, there will be something around nearest neighbors also. That will also will take something from the match outcome prediction. So you can compare two different algorithms, how it is supporting for the data set, and why this naive Bayes is giving only 0.51 percentage, while this is actually giving you 0.65 percentage. You can actually compare and show. If needed, you can also plot the accuracy chart for this particular naive Bayes also, right? So this is 5.1, and over here it is 0.64, nearly 0.65, I can say. So 14% is higher over decision trees, right? So so if I'll go to, so I want you guys to update this also inside your collab, and I want you guys to update your lab manual up to this naive Bayes algorithm, that is up to 5th exercise. So this is the middle exercise we have. So after this middle exercise, you update and you put it inside our Google Classroom, right? So this came in actually from the next unit. So we'll have a different kind of data set and problem statement for this k nearest neighbors. Sorry, k means. Then we have many kind of clustering algorithms to do over here. Then k mediad is there. DB scan clustering is there. So how for a single data set different clustering algorithms will work. Then SVM is available. So you can also, if you want, you can also try SVM for the same outcome prediction also and see how the percentage is actually differing. So finally, we then so 11th exercise, I hope this is PCA is there for real-time object detection. I think PCA is already done by Abhiram and team for their RBE last time. So those things, right? So this particular base one, you have to run this entire algorithm, entire cells. Hope you know the Colab will actually delete the history. So you have to run each cell again, and you should come back over here.